Welcome everyone to the IRENA seminar series, where today we've got Dominic Bowman from Newcastle University. So I'm Erin Higgins, a Leverhulme Fellow at Queen's University Belfast, and I'm the representative for Bridge C, the UK network. And so just a bit about Dominic, our speaker today. Dominic completed his PhD in astronomy at the University of Central Lancashire under the supervision of Professor Donald Kurtz, and then he moved to the University of KU Leuven as the postdoctoral researcher in the team of Professor Connie Ertz, and then was later awarded an independent FWO research fellowship. And then since September 2023, Dominic has held a readership faculty position at Newcastle University, and he is a PI of a Royal Society University Research Fellowship and also of an ERC Starting Grant with the project Symphony. And so I'm sure we'll hear more about that through today's talk. So take it away, Dominic.
Thank you very much, Erin, and thank you everyone for giving me your time. It's a pleasure to talk to such a diverse and learned colleagues as always. So I make no apologies for the title of my talk. It is intentionally a pun of the grant symphony that I'm going to talk to you about today, and just a little bit about the broader context of what this seminar is about. It's about stellar pulsations, and these are diagnostic probes of the physical processes that take place inside stellar interiors. So I tend to work in a broad area of the HR diagram with stars that are typically blue in color and masses of about 10 times or more the mass of the sun. So these massive stars are supernova progenitors. They end their lives in compact object form, for example, neutron stars and black holes. And they're generally good laboratories for testing various different aspects of physics. So they have energetic, radiatively driven winds. They're commonly formed in binary systems. Some of them have magnetic fields, particularly strong magnetic fields that are at the surface. A large fraction of them pulsate, and very often they rotate very rapidly. So this gives us lots of different aspects of physics that we can test in a relatively small-ish size on the HR diagram. So here's a bit of an outline of what I'd like to talk to you about today. So I'll give you a bit of an intro of the physics that I'm interested in, and then what asteroseismology actually is. So that's the main tool or the method that I use to probe these physical processes. Some results from that, and then I've put a little bit of a focus on magneto-asteroseismology. This is an emerging field where we can actually probe the interior magnetic fields of stars. And then finally, a little bit of a subject that's close to my heart, which is how we can look at the stochastic processes that take place in massive stars as well and learn about their interiors from that. So as mentioned, there's some physics that is prevalent in the massive star regime. So I've broadly categorized it here as three different types. So stars in the massive star regime are rotating very fast. So these are large fractions of their breakup velocity. So this means that the star generally is distorted. It is no longer a sphere. And inside that spherically distorted star, you'll have processes that lead to efficient mixing. And that mixing process will take core process materials such as nitrogen to the surface, and it will also replenish hydrogen into the burning core during the main sequence phase of evolution. So that means the star can live longer. So for different metallicities and different rotation rates, a figure here on the left showing the path that the star will travel through can be quite different. So if you're able to measure the effective temperature and the luminosity of one of your stars, it's a bit of a degenerate parameter space because you don't really know what the rotation frequency of the star is. You have a constraint, but really we want to know what the interior rotation frequency is, or the profile, the radial rotation profile. Massive stars also lose a lot of material through winds. So we have a bit of a problem in that we have some predictions of what the mass loss rates of massive stars should be. There is a sensitivity to the metallicity. So it's massive stars that are in the large and small Magellanic Cloud have lower mass loss rates. But there's a problem that's been referred to in the literature as the weak wind problem, which affects B-type stars, these early B and late O-type stars, in which our predictions are quite considerably off from what the observed mass loss rates are. And then finally, binarity. We know that from spectroscopic surveys now that cause radial velocity motions in the spectral lines of stars as they orbit each other, that effectively the majority or even the vast majority of massive stars are born with a companion object. There's some wiggle room on what the orbital period is and the mass ratio, but generally speaking, most of these massive stars will interact with their companion. They'll exchange mass, angular momentum, and this will change their evolutionary fate. Specifically, I've mentioned mixing as a consequence of, for example, rapid rotation, but where asteroseismology really comes into its own is being able to probe the size of convective regions, specifically on the main sequence that would be the convective core, because at that boundary, there's a very strong boundary condition for the pulsations that exist inside stars. So for people who work on explosions, what really matters, I'm told, is that you care about how much helium there is in at the core of a massive star at the end of the main sequence, and this is a deliverable of asteroseismology. But the consequence of not having very good prescriptions for mixing and rotation inside our 1D stellar evolution models is that stars can have, as I've mentioned, fairly exotic paths through the HR diagram. So on the right here, I'm just showing you what's been known as a blue loop, in which stars, once they've reached the top right-hand part of the diagram here, they will, for a small but significant amount of time, return towards the blue, in which they can be core helium burning before becoming a red supergiant for a second time. So again, if you were able to find a star in this Hertzsprung gap, which should be a very short phase of stellar evolution, you need to have some physics that's keeping it there. We find far too many stars in this Hertzsprung gap, and so the Symphony project is targeting specifically these stars to understand their interior rotation and mixing parameters so that we can provide to the wider community deliverables such as the core mass. So now on to the tools of asteroseismology, the types of pulsations and the types of pulsators that we have to deal with. But first I wanted to start with the data. I'm an observational astroseismologist, as my colleagues sometimes call me. So I take a data-driven approach. So the pulsation frequencies are revealed through the Fourier transform of time series data. And the most readily accessible data sets that we have, thanks to a space photometry revolution driven by our exoplanet colleagues, are from, for example, the NASA Kepler mission, the NASA TESS mission, and soon the ESA Plato mission. So in the top panel here, I'm showing you a light curve of a pulsating massive star. The scatter is real. This is the oscillations of the star causing the light from the star to fluctuate up and down, and the error bars are smaller than the symbol sizes. Now, if I take the Fourier transform of the first 90 days, I see a relatively broad peak, and this is the one-dimensional result of the Rayleigh criterion for resolution. If you've done any sort of imaging where you're trying to image two stars on the sky, that's just the two-dimensional equivalent. But if I take more and more data, the resolution of the data is improved, the peak gets narrower and narrower. So it's only with 4 years of data, which is the entirety of this light curve, that I reveal there are in fact two pulsation peaks that are very close to each other that are causing this envelope of beating on a timescale of years. So this is why asteroseismology has really been revolutionized through our space mission photometry, through exoplanet colleagues, because we had to wait several years to actually have the resolution to resolve these individual pulsation mode frequencies. And it goes without saying that the precision on the pulsation frequencies scales as the resolving power of the data set as well. So the higher the precision on the frequencies, the higher the precision we can get on the parameters of the star. There are two main types, not exclusive here, but the two main types of pulsations are the gravity modes. So these are restored by buoyancy. So if you just take a cork and displace it below water, it will naturally oscillate around its equilibrium point, which is the surface. And the same is true here for a parcel of gas inside a star. If you give it a little kick, it will oscillate around that point. And then the other type is the pressure modes. These are sound waves. And they are restored by the pressure gradient. Now, ideally, we want to find stars that have both types of modes because they are sensitive to slightly different areas within a star. The G modes are quite sensitive to the near core, and they have the property that they are evanescent in convective regions. So they're very sensitive to that convective core boundary. And that's why we're able to measure the size of the convective core and the mass that it contains. And the pressure modes tend to be more sensitive to the surface layers, so the radiative envelope in these massive main sequence stars. And therefore, if we get both types of pulsations, we're able to probe the physics as a function of the radius in a given star. You'll also notice that there's some characteristic patterns, and this is the method by which we identify the pulsation modes in terms of spherical harmonics, which are a little bit more in detail here. So because rotation is a perturbation to the pulsation frequency in the same way that we have a Doppler shift from the passing ambulance, the degeneracy of non-radial pulsation modes is lifted through the Coriolis force. So you can see on the left here for light curves of different lengths, 1 year and 4 year light curves, you see a quintuplet. These are 5 individually spaced peaks, and they constitute the allowed azimuthal order values for a given L. So we have 5 frequencies, so we can count the azimuthal orders of m equals to -2, -1, m of 0, m of +1, and +2. So we've identified a quintuplet, we've identified a quadrupole, L equals 2, and we can apply this relatively straightforward the first order Ledoux splitting equation to measure the interior rotation frequency, which is responsible for splitting those frequencies. The faster the rotation, the larger the splitting. And this is effectively a model independent measure of the interior rotation of a star. The gravity modes have a characteristic period, and in the asymptotic approximation, which means if I go to very high radial order, they have a flat pattern in what we call the period spacing pattern. And this is the difference in period of consecutive radial order G modes as a function of the period. Now on the right here, I'm just showing you as a star is born near the zero-age main sequence, and as it evolves, I've highlighted a couple of different steps in the evolution path here, the morphology of that period spacing pattern goes from being relatively flat to having structure. Now, for stars that are chemically homogeneous and non-rotating and non-magnetic, brackets, no such thing exists, you'd expect a completely horizontal line in this period spacing pattern. But as the star ages, the convective core in a massive star will shrink, and it leaves behind a gradient between the hydrogen and the helium abundance. And that is a contribution to the Brunt-Väsala frequency profile inside a star, which has both a thermal contribution and a chemical composition contribution. So as stars evolve and that core shrinks, it introduces wiggles and dips in the period spacing pattern, and this is how we're able to use the pulsations of a star to constrain its age. And correlated to its age would also be its mass, its core mass, etc. So we've got rotation from the splittings, and we've got the age and the mass and the fundamental parameters from these gravity mode period spacing patterns. So on the different types of pulsators that we have available, I roughly speaking work within this green shape. And this covers a mass range of about 3 solar masses upwards. There in principle is no upper limit to pulsations on the main sequence. And then also within the post-main sequence in this so-called Hertzsprung gap, there is a third type of pulsator, which we have started calling stochastic low-frequency variability. Now, the types of pulsators are generally named after either the first star that showed this type of variability, like Beta Cephei, or a renaming of the group for various acronym reasons. But generally speaking, the Beta Cephei stars have both P and G modes. These are so-called hybrid pulsators. They are the subject of the Symphony project. And then at lower masses, we have the slowly pulsating B stars, which are effectively pure G mode pulsators. So let's have a look at what we've learned from applying asteroseismology in this rough part of the HR diagram. And the method that we use, we identify the pulsations through frequency analysis, and then we do a data-driven approach where we compare the observed pulsation frequencies to a grid of theoretically predicted frequencies within the HR diagram. So just to show you what that looks like in principle, there's a little sketch on the left here, which is a one-dimensional representation of what the interior of a star might look like. You have the convective core in gray with very efficient and very instantaneous mixing. You have some boundary region, so this is the convective boundary mixing zone, which can take on the shape of an exponential here, or it could take on a step, or it could take on both. These are all free parameters that we can test. And then you have some amount of mixing in the envelope, which is either driven by rotation if it's a rapid rotator, or it could be driven by waves or shear or any other combination of the different physical prescriptions. So you put all of those different prescriptions into a grid of models, and you calculate the grid. And I'm showing you here some results from papers by Ehsan Moraveci, who was the first to do this using the MESA and JIA code. Each colored circle here represents an individual model of a star. There are many millions of models in this plot, and they have been color coded by the goodness of fit relative to the observed pulsation frequencies. So each theoretical structure model is perturbed using the JIA oscillation code, and that gives us the theoretical pulsation frequencies. If you want to know a little bit more details about what the shapes of these boundary mixing zones look like, there's a few papers here that I show you for a few or samples of stars. Generally, there's a great diversity we've found. There's no one size fits all. It's not that all stars have a step overshoot of the exact same value. There are hints that this is mass dependent and age dependent, and we're also now able to constrain what the temperature gradient is inside that zone. So is this a penetration zone, or is this an eddy dominated mixing zone? On the results for rotation, I'll bring you down in mass just a little bit because I wanted to show you the results for all rotationally studied stars across the entire HR diagram. So this goes down to the lowest mass dwarfs and even red giants. On the left here, I'm showing you as a function of the log G of a star. So stars are born on the left of the diagram and they evolve to the right. And on the y-axis is the interior, the core or the near core, dependent on the type of star, rotation frequency. The dwarfs are in green, the red giants and red clump stars are in red and blue respectively. So as stars evolve, they have this sort of linear trend that's expected. But you can see that within a different type, within the same type of star, there's a bit of scatter here. That's okay. But in the middle panel, I'm overplotting the envelope rotation frequency as a triangle. And you'll notice that for most of the main sequence variables, the circles and the triangles fall pretty much on top of each other. This means that stars of relatively high mass, so somewhere around 5 to 8 solar masses, and for a full range of rotation frequencies, are effectively rigid body rotators. This was very unexpected when this result came, and some papers down here to read more about this. There's an excellent review from Connie Ertz on angular momentum transport and the explanations for this. But there seems to be an extremely efficient angular momentum transport mechanism extracting angular momentum from the core, redistributing it throughout the star on short timescales, which causes this rigid rotation. But you may have noticed that the triangles do not fall on top of the circles when you go to later evolutionary stages, and there is about 1 order of magnitude difference between the near core or the core and the envelope. However, this should be about 3 orders of magnitude difference. Remember that as stars evolve off the main sequence, they become large, the core becomes extremely compact, and so you'd expect the core to be spinning very fast and the envelope to be spinning very slow. So there should be about 3 orders of magnitude difference between here, but there is only about 1. Interestingly, it gets even smaller again, so it's about half an order of magnitude when the star has a convective core that's burning helium. So what we think is that either it is the convective core triggering waves, or you have some sort of Taylor-Sproat dynamo that is enacting when there is a dynamo-generated magnetic field in the convective regions of said stars. Because the angular momentum transport is very efficient in the red clump phase when there's core helium burning, and in the main sequence, which is the hydrogen core burning phase. On the third panel, I just want to highlight that this is specifically for the massive stars. So the most massive star as of right now that has been modeled with forward asteroseismic modeling is about 25 solar masses. And there are only about 6 points in this plot. So one of the deliverables of the Symphony project, if you invite me back in about 4.5 years, is hopefully that we're going to have populated this panel with about 100 stars. As you can see that it's a bit difficult to draw any conclusions because we have a couple of stars that appear to be rigid and a couple of stars that are differential in their radial rotation profile. So the jury's out on if this is ubiquitous across the entire HR diagram, and how the physics of this operates. So on one star in particular, so this is a massive star that was a study led by my former PhD student, Simon Bursons, that we published a couple of years ago. This was observed by the NASA TESS mission. It has this beautiful, pristine 1-year light curve, as I'm showing you a section in the top right, and the frequency spectrum of that light curve is shown in the bottom right. And if you've remembered the rotational splitting diagram that I showed you previously, where rotation splits modes into various multiplets, you might start to convince yourself that you can see some equally spaced frequencies. And there are a series of multiplets in this star, and the more multiplets we have, the better, because they are sensitive to different parts of the interior, allowing us to build a profile from the surface to the core on the rotation, but also the density, etc. So we did a forward seismic modeling approach, and we used, instead of the simplistic chi-squared merit function, we used what's known as the Maller-Hanobis distance. This includes the uncertainties from your theoretical grid, and this was the first time this was applied to a massive star in the context of forward astroseismic modeling. So it gives you the advantages of including the degeneracies and the correlations that exist between parameters, such as mass and core mass, luminosity and temperature. These are very correlated parameters, as we know. And it builds into that merit function a penalty so that you aren't ending up with large banana-shaped posteriors, but well-constrained parameter distributions. The 2 sigma confidence intervals for this particular star are shown on the left. You can pick your favorite parameter. I think the one that is of interest maybe mostly for this group is the core mass of the star and the initial mass of the star are known to of order 10 to 20% precision. And as I said earlier, if we have more and more test data, which we do now, we've observed this star for over 5 years now, the precision on these parameters will only get better every single year because these parameters were determined from only the first year of test observations. We also, for the first time, as I mentioned, not only used the Maller-Hanobis distance, but we were able to incorporate a Monte Carlo-like sampling to get posteriors of the parameters in a robust and slightly more sensible way than what was done in the past. So this is just to give you a distribution, or this shows you the distribution of what the core mass values look like, and you can chi by eye if you want to what the sort of uncertainty looks like. So remember that this is a grid of models, many millions of models that are built within the HR diagram to cover the range that we would expect, and they are perturbed using the JIA code to predict the theoretical frequencies, which are then compared in a statistical framework to the observed pulsation frequencies to extract parameters, such as the interior rotation and mixing. On the right here is just showing you what the profiles of the diffusion coefficient. So in brown here is what the convective core size is. In green is the envelope, and in gray is the boundary mixtion zone. And on the bottom, again, for the first time, we tested different assumptions in what the shape of the rotation profile could look like inside such a star. Previous studies, of which there are only a couple, have just assumed there is no shear layer between the convective core and the surface, and for example, just taken the cyan model, where you have just a constant slowing down of the star as you go from the core to the surface. But we know from hydrodynamical simulations of stellar interiors that when you have a convective core boundary, there should be a very strong shear layer between the overlying radiative envelope and the convective core. You'd also expect potentially quite strong differential rotation in that region because of the shear, and as I'll come on to in a moment, potentially a magnetic field as well. So by testing these different prescriptions for what the shape of the rotation profile, and by sampling across the entire grid, which includes the theoretical uncertainties, we're able to ascertain what the best model for the rotation profile, the radial rotation profile, looks like. And it seems to be this yellow one here, which means that we have a core to envelope rotation frequency ratio of about 1.5. Remember that these are stars that are beyond the zero-age main sequence. The core has contracted, and so we would expect it to be rotating much faster than this. It should be rotating about a factor of 10 higher in the core than in the bulk of the envelope. So there is some sensitivity. Obviously, the purple has a much stronger shear layer, if that is the best solution. But this is still a relatively low number. So again, there's a very efficient angular momentum transport mechanism needed to reproduce these results. Now, I mentioned magnetic fields, and I told a little bit of a white lie earlier about when I said there were three types of physics that we were trying to constrain, which is the rotation, the mass loss, and the binarity. Most of the time, we try and pretend that magnetic fields don't exist. I think this is the elephant in the room. But very recently, we've actually been able to look at the magnetism that takes place in massive stars. Now, we know from spectropolarimetry that we have about 10% of our massive stars with a strong, stable, and large scale, i.e. a dipole magnetic field at the surface. And if you propagate that dipole throughout the interior, this has big consequences for the spin up or slow down and the transport of angular momentum inside stars as they evolve. There are two main hypotheses for, and these are not mutually exclusive, for how you make such a strong field, which is the fossil field hypothesis, which is that there is a seed field in the protostar that, when it's collapsing, amplifies onto the main sequence. And I should mention here that strong here means of order a kilogauss in terms of a dipole field, which is pretty strong compared to stars like the Sun, for example. You can also make magnetic fields through binary mergers. So there's been work by Fabian Schneider on this. But of course, we know that the binary fraction of massive stars is very high, but the incidence rate of magnetism is relatively low. So there's work to be done on which of these two mechanisms dominate in which parts of the parameter space. So I'd like to show you a star here for which we've done forward astroseismic modeling, but specifically, it's the only one for which the surface magnetic field, which was measured through spectropolarimetry, was incorporated into the modeling. So it has been measured to have a fairly fast rotation rate for a magnetic star of about just shy of a day, and it has about 1.3 kilogauss dipolar field at the surface. So if you extrapolate that inwards, assuming a dipole, you'd expect something like 10 to the 5, 10 to the 6, if it's a pure dipole at the very center of the star. And not including any knowledge of dynamo-generated fields because of the convective core. So we get a mass, and we get an age, and we get a core mass, and all the other parameters I've mentioned previously from our forward seismic modeling, and that gives you a region in the HR diagram. You can see that it's relatively young. It's still quite close to the zero-age main sequence. But what caught our attention about this star is that it has unusually low radial order gravity modes. In most of these types of stars, the radial orders are 50 or 60. But this one literally has 1, 2, 5, 6, 7, etc. So this is a bit unusual, and it led us to the hypothesis that maybe the magnetic field that we detect at the surface is, a reasonable assumption I would say, extending into the interior and interacting with the pulsations and suppressing the high radial orders that we would normally see, leaving only the low radial orders left. So there are a couple of different theoretical works that have been done on how magnetic fields interact with gravity waves. You can perturb the frequency in the way that rotation perturbs and splits modes into multiplets. This can also happen from magnetic fields, but they'd have to be extremely strong. And we've just recently, in the last year or two, been able to start detecting these magnetic fields through splitting for red giant stars, for example, but I won't talk about that today. But you can also, for example, suppress the excitation mechanism. So if there's some mechanism that excites, for example, if there's convection, magnetic fields will suppress convection. So maybe you just wouldn't see the pulsations. Or you could damp individual waves because they interact and you get a wave-wave interaction. So there's been some analytical work on this. And so the formula on the right just says that if you have a frequency that is below the magnetic interaction frequency, which is FB, you wouldn't see it. It will convert from a gravity wave into an Alfvén wave, and therefore we would not see that particular frequency at the surface of the star. Just to plot what that looks like for this particular magnetic pulsator, the Brunt-Vasala frequency profile, so the buoyancy frequency is shown in blue. We see gravity mode frequencies that are typically around the green line, and you can calculate for the given model what the interaction frequency is. And you can see that they're quite close. But so we asked the question, well, what is the highest magnetic field strength that we could hide in the deep interior before it would suppress the pulsations that we do see? So this sets a very strong upper limit on what the near core magnetic field strength could be in this star. And it turns out to be about 5 times 10 to the 5 Gauss at the fractional radii of 0.18, which is right in this Brunt-Vasala frequency spike here. So this is completely reasonable, I would say. But just to prove that to you, the study led by Daniel Lecoine, which we published a couple of years ago, he's an expert in the Daedalus code, which is an MHD code. And so he ran some rotating MHD simulations and solved this wave-wave interaction problem. So on the left here, I'm showing you what the azimuthal velocity structure of the star would look like for the 15th radial order. Apologies for the jargon. If I was to slice through the equator of the star. And you can see the radial orders, you can count them, they're the white zones here. So you've got 1, 2, 3, and different parts of the star are oscillating. The next radial order, of course, this is an integer, is the 16th. And you can see there's you've squeezed in one more radial node here. However, for the given model, for the known rotation and the known surface magnetic field strength, you can calculate what the outgoing wave structure would be. And we can see that the 16th radial order completely interacts with the magnetic field and creates an Alfvén wave, which we don't see at the surface because it doesn't cause flux variability that we would detect like a G mode. But the 15th radial order that we do see doesn't interact. So this is effectively like a switch. The modes encounter an increasingly strong magnetic field as they travel inwards. And if they have their frequencies below that interaction frequency, they aren't able to travel back out again. So you could be ejecting as many gravity modes into the interior as you want, but they're completely trapped because they're converted into Alfvén waves. Is this reasonable, the value that we've got? We think so, because if you run MHD simulations of core convection, in the presence of a fossil magnetic field, you get about 10 to the 6. And if you run a self-excited dynamo-generated magnetic field without a fossil field on top, you get about 10 to the 5. And we're about in the middle there. So that's probably not coincidence. So what we think is we're finding is that in the magnetic field that we're measuring just outside the core, which of course used to be part of the core, is the remnant of the dynamo-generated magnetic field that's amplified a little bit because there is a fossil field that's predominantly dipolar permeating through the entire star as well. So this is the first time that this was done by setting an upper limit of what the magnetic field could be inside a magnetic pulsator. And as I mentioned, we're starting to do this for other parts of the HR diagram, such as red giants, but these are much lower mass than I tend to work on. So in the last 5 or 10 minutes, I'm going to talk about my fifth topic, which is that we have this space photometry revolution that has undergone thanks to our exoplanet colleagues, but we've discovered lots of different types of variability. And up until now, I've been talking about coherent pulsation modes that have a unique frequency and a unique spherical harmonic geometry. And they appear as effectively Dirac delta functions in the frequency spectra of pulsating massive stars. However, one of the things that we've discovered in recent years is that modes are not as coherent as we thought they were, and they tend to be a little bit more stochastic and turbulent. So on the right here, I'm showing you a light curve and a Fourier transform of a typical massive star that was observed with the K2 mission, the NASA Kepler second generation mission. And on the left, I'm showing you a snapshot. Well, it's not a snapshot, it's a little movie of a hydrodynamical simulation of about a 25 solar mass star by Herwig and collaborators. And on the bottom here of the observations and to the right of the simulations, we have the frequency spectra, which I fitted with a very simple parametric semi-Lorentzian to try and understand the strength of the stochasticity in the light curve or the time series from the simulation and parameterize it with some sort of typical time scale, amplitude, and parameters like that. Now, the jury is still out about whether the consequence of the turbulent core convection exciting gravity waves, which you can see in this sort of cyan color here, and whether that signal actually reaches the surface. I believe that we have strong evidence that it partially does, but there are other works in the literature, so I've of course sort of color-coded them here that have put forward different explanations. And I think my conclusion in the last 12 months here is that it's not about a one or the other. I think it's about trying to constrain which parts of the parameter space have a dominant mechanism. Because, for example, core convection doesn't occur when you don't have a convective core. So if you're in the post-main sequence Hertzsprung gap, and your shell hydrogen burning, this is a different parameter space. If you're a Wolf-Rayet star and have optically thick winds, then the photometry that we're gathering for such a star is actually the variability in the atmosphere rather than the deep interior. So it's about trying to put all these pieces together and constraining the importance of these different variability engines, these mechanisms that take place. So in addition to the convective core, driving gravity waves that are stochastic and reach the surface with variable amplitudes that explains this stochastic low frequency variability in green. We could also have convection near the surface, so-called subsurface convection zones, and we could also have optically thick winds that cause turbulence that we see in the light curves as well. So part of what we're trying to do in the Symphony project is disentangle all of these different types of variability mechanisms and say where they dominate in parts of the HR diagram. Now, one of the issues that we have with subsurface convection, for those of you who work on hydro simulations or stellar evolution models, is that convection in a 1D stellar evolution code is a little bit of a parameterization. There are various ways to define it. But we do know that convection is a very metallicity dependent process. The lower the metallicity, the harder it is to have convection. Similarly, the faster the rotation, the harder it is to have convection, because rotation is has a stabilizing effect against convection as well. So for a sample of galactic massive stars, we were able to probe how this stochastic low frequency variability changes throughout the HR diagram. And so hopefully you can see here that as stars go from the zero age main sequence towards the terminal age main sequence, they've been color coded here from this purple to this yellow color, and that is the characteristic frequency of the light curve. So that's promising, because it means that just from a light curve and without any real constraints from spectroscopy or interferometry or what have you, we can get a first order estimate of how old the star is. More recently, I've developed a Gaussian process regression model with the Celerite code of Danforth and Mackey to try and look at the stochasticity or the quasi-periodicity, dependent on your optimism or pessimism of the day. And we find that the quality factor it also transitions. So if you model this process as a damp simple harmonic oscillator, the quality factor tells you how periodic the waves are. And that also transitions. Stars are born as very stochastic variables, and they start to become quasi-periodic as they approach the terminal age main sequence. So again, another way of probing the variability in massive stars, which we wouldn't normally get if we were just looking at Fourier transforms and frequencies, individual frequencies. So as mentioned, people have run very sophisticated hydrodynamical simulations of what the envelopes of these massive stars could look like. And so I'd like to highlight some recent work here from the KU Leuven group, so a paper by Debnath, 2024, who has shown that the envelopes of these so-called subsurface convection zones actually may not be convective at all. They are radiation dominated, and the turbulence, some sort of instability that is formed, is potentially responsible for driving the winds in these stars, but it's most likely, in their paper, they conclude it's a Rayleigh-Taylor-like instability, which creates large velocity fields, which has been known about for a long time in spectroscopy. This is a parameter that we call macroturbulence, which is a velocity field that is much larger than the mean free path of a photon, and microturbulence, which is small scale, a little bit more isotropic, and that's on scales smaller than the mean free path of the photon. So we've needed this in spectroscopy for many decades now to explain the shapes of spectral lines. In the dotted profile here is if you only have rotation as a broadening mechanism, and it's a bit hard to see, but the gray dashed line is if you include macroturbulence, which often in massive stars is higher. Here it's twice as high as what the V sin I is. So the velocities at the surfaces of stars are not dominated by their rotation. They're dominated by some self-excited turbulence, such as the Rayleigh-Taylor instability or the core-excited gravity waves I mentioned on the last slide. So to try and figure out where this stochastic low frequency variability came from, we set out using a theory from Adam Germain in a couple of years ago, where if you parameterize convection not from just the Schwarzschild criterion, which is a little bit simplistic in my opinion, you can use various dimensionless numbers, such as the Rayleigh number, to parameterize whether convection is taking place or not. And this is just a measure of whether buoyancy or diffusion wins within the envelopes of a massive star. And if a star using the Rayleigh number does not have a subsurface convection zone, it has been labeled in the blue in the HR diagram on the right. And plotted over the top of that is the red points, which are stars from the X-shoot-U collaboration for the Small Magellanic Cloud. So there is a relatively large parameter space according to one-dimensional Rayleigh number specified convection evolution models, which should not have stochastic low frequency variability if it comes from a subsurface convection zone, because such a zone is predicted not to be there. Remember that we're at low metallicity here, so convection is very hard to excite, especially when you're rotating and at a metallicity of the SMC. So we asked the question, well, do the stars that are within the region have different properties to the stars outside of the region? And these are substantially different masses and ages. And we did this by looking at a well-characterized sample of X-shoot-U stars using the TESS mission. And so in a paper from the end of last year, we studied the stochastic low-frequency variable properties. And I don't have time to go into the details here, but generally speaking, the SLF amplitude is ever so slightly weaker for the stars that are within the blue region. It's about a factor of 2 or so, but the scatter within the stars is about 2 orders of magnitude. So it's not statistically significant between the two groups, but within the group, the variability is the variance of the variability, that's hard to say, is quite high. So I'm just showing you a few examples here of what these stars look like. It's quite a challenge. Test data for the Small Magellanic Cloud was never on the mission documents of the NASA science team, but the data are excellent, and we've been able to use a PSF fitting approach using the TESS-GAIA light curve package of Hannon Brandt to extract light curves of high quality. So I'm coming to the end, so I'll just conclude. So I've talked about asteroseismology of coherent pulsators, the rotational splittings, and the period spacing patterns that allow us to look at the interior rotation from anything pretty much from 0 up to a very high fraction of the critical breakup of massive stars across a wide range of masses and ages. We've looked at the boundary mixing and the envelope mixing and been able to deliver for samples of stars what the core mass is, for example, the amount of helium that we have in the center of the star. And for one, and hopefully more in the future, we've been able to put a very strong constraint on the an upper limit on the magnetic field in the near core region, which is consistent with hydrodynamical simulations of that star. The SLF variability that I've mentioned is an independent measure of the masses and ages of stars. And so in the Symphony project, we've been looking at the main sequence up till now, but the time is now really to push beyond the main sequence, try and figure out what sets the terminal age main sequence, which is still an unknown, and why do we find any stars in the Hertzsprung gap, because they should evolve extremely quickly to the red supergiant phase. And so with that, I will end. Thank you for your attention. I'm very happy to take questions.